Let us start another question answer session on mechanics, and this is lecture number 4. We shall try to solve the following question. A particle of mass m is projected with initial velocity u at an angle alpha with the horizontal. Use Lagrange's equation of motion to describe motion of projectile. Neglect air resistance. And this is a very important constraint or condition that will make the problem very simple. We come to the answer now. This is x-axis, this is y-axis, this is the origin denoted by O. Let this vector along this direction represent vector u, the initial velocity. Obviously, it makes angle alpha as per the question. And this curve, say, represents the path of projectile. This represents mass of the projectile m. Let us write down the parameters describing the projectile at one place, and here it is. Mass is m, initial velocity is vector u having angle with x-axis as alpha, and x-axis is the horizontal direction. Generalized coordinates are x and y. Now kinetic energy is T equal to half mv square, which is equal to half m into x dot square plus y dot square. Potential energy is V equal to mgy, where let us choose V equal to 0 at y equal to 0. Lagrangian is L equal to T minus V. So let us write down the expressions of T and V with a minus sign in between. Now the Lagrange's equation of motion in the generalized coordinate x is d dt of del L del x dot equal to del L del x. Plug in the expression of L that we got, and this gives consider this part involving del del x dot, performing which we get mx dot. And look at this part involving del del x that gives 0 as no x occurs within the bracketed portion. The left hand side is d dt of mx dot. M is constant, so we essentially have d dt of x dot, that is x double dot equal to 0. Multiply both sides by dt to get, integrate, dt cancels out, and we have a constant a, which is a constant of integration. So dx dt is a. Multiply by dt on both sides and integrate to end up with, here b is another constant of integration. Lagrangian equation of motion in the generalized coordinate y is d dt of del L del y dot equal to del L del y. Plug in the expression of L to have now focus on this part involving del del y dot that yields my dot, and the right hand side is minus mg. So we have m cancels out as it is a constant. This is what we get. Multiply both sides by dt. Integrate to get, here c is a constant of integration, dy dt equal to minus gt plus c. Multiply again by dt on both sides and integrate. And now we get another constant d in the process. The equation we end up with is y equal to minus gt square by 2 plus ct plus d. We collect and write down the solutions we derived by solving Lagrange's equation of motion, and they are x equal to at plus b and y equal to minus gt square by 2 plus ct plus d, where a, b, c, d are constants to be determined. And to determine them, we apply boundary conditions, which are the initial conditions that caused the projectile to move along a path. projectile was projected at t equal to 0 from origin, that is from the point x equal to 0, y equal to 0. Consider the x equation and apply the condition that at t equal to 0, x equal to 0, that gives b equal to 0. Now consider the y equation and apply the condition that at t equal to 0, y was 0 to get d equal to 0. With a equal to 0, d equal to 0, let us rewrite the position equation, and they are x equal to at, y equal to minus gt square by 2 plus ct. Note that we still have the task of finding two more constants, namely a and c. This we do by exploiting the initial velocity condition. Let us first find the velocity at any time from the position equations using the definition that velocity vector is d dt of vector r. Component wise we write Vx equal to x dot equal to dx dt, which is a, and Vy equal to y dot equal to dy dt, which is minus gt plus c. The velocity equations are: apply another boundary condition, namely the initial condition that the projectile was projected with initial velocity vector u at t equal to 0. This is x-axis and this is y-axis. We show at t equal to 0 the velocity vector u that the projectile was thrown with. This angle is alpha. Along x-axis, the initial velocity vector u has component u cos alpha, and along y-axis the component is u sin alpha, all at t equal to 0. Let us write it Vx equal to u cos alpha and Vy equal to u sin alpha at t equal to 0. So Vx equal to a, with the condition that at t equal to 0 Vx equal to u cos alpha becomes Vx equal to a equal to u cos alpha, and Vy equal to minus gt plus c, with the condition that at t equal to 0 Vy is to u sin alpha becomes Vy equal to c equal to u sin alpha. We have thus, with the initial conditions on velocity of projection, obtained the constants a and c. And now we write the velocities Vx equal to u cos alpha and Vy equal to minus gt plus u sin alpha. This holds for any time t. These are the velocity components. The position components are x equal to at, y equal to minus gt square by 2 plus ct. Putting the values of a and c, they become x equal to u cos alpha into t and y equal to minus gt square by 2 plus u sin alpha into t. These are the position components and they hold at any time t. Eliminate t from these two equations. From t is x by u cos alpha. Putting it in the expression for y, we have denoting this quantity by b and this one by a, we can rewrite the t eliminated equation as y equal to ax plus bx square, which is the equation of a parabola. So projectile follows parabolic path if air resistance is neglected. This is the parabola which the projectile follows. This is x-axis and this is y-axis, this being the origin.